Okay, so we've looked at how to find limits from a table and limits from a graph, but both of those methods have their limitations. Sometimes it's kind of hard to tell from a table or from a graph what the limit should actually be. So we're going to actually now start talking about how to find them algebraically. So we're going to look at this first example. We have this function, f of x equals 1/2 times the absolute value of negative 2x plus 4 minus 4, and the graph's pictured over here. And so we're going to fill in this table, and we're going to find the limits two different ways. So we're going to start off by finding f of a using the equation. So a is the number that x is approaching, and we're going to find f of a by just plugging that number into the function. So if you type that function into your calculator, into F1, then we can plug into that equation by just using the var key, typing in the number we want to plug in. So when we plug in 0, we get negative 2. So we plug in 0, we get negative 2. Now when we look at the graph, as we approach 0 on the graph, you can see from both directions we arrive at a height of negative 2. Right? So now we're going to plug 2 into the equation and see what happens. So let's look and see if we plug in 2. We get negative 4. Right? So plugging in 2 gives us negative 4. Well, when you look at the graph, as you approach 2 from the right, we arrive at negative 4. Last we're going to look at is as x approaches 10. So if we plug 10 in, we get 4. So if we look at the graph doesn't go all the way out to 10. Oh wait, sorry, I forgot to fill that in. The graph doesn't go all the way out to 10, but you can imagine what would happen if it did, right? This is going up 1 over 1 as you move to the right. So starting here, if you went up 1 over 1, up 1 over 1, up 1 over 1, up 1 over 1, till you got to 10, 7, 8, 9, 10, you would be at a height of 4. So when a function is defined, right, that means it doesn't have any holes or asymptotes, and continuous, right, again, no holes or breaks or asymptotes, then you can find the limit by just plugging in, right, plugging in this value in the function, right. So underneath here are some examples that you can work. You just plug in. So I'm going to actually pause the video and go ahead and work these through. I encourage you to do the same thing, and then I'll kind of run back through them real quick. Okay, so if you plug in on each of these are the values that you should get. So the first one, you plug in 3, you should get 3/2. Part B, you plug in 3, you should get 17/3. Part C, you plug in 2, you should get 1/3. Part D, you plug in pi over 2, and 2 times pi over 2 is going to be pi. And so if you look at the unit circle in your notebook, the sign of pi is negative 1. If you plug in 2 pi over 3, the cosine of 2 pi over 3, if you look in your unit circle, is negative 1/2. And then you're dividing that by 2 pi over 3, so you have to keep it, change it, flip it. So you would keep the negative 1/2, change it to multiplication, flip the 2 pi over 3. And so you should get negative 3 over 4 pi. And then the last one, if you plug 9 in, you get log base 8 of 2. And remember, a log is asking you what power of the base is this number. So 2 is the cube root of 8. And remember, a cube root is a 1/3 power. Okay, so now we're going to talk about some cases where this plugging in doesn't work. So if you go through and you try the plugging in method on these 3 examples, you're going to get, when you plug negative 3 in, you're going to get, let's see, 9 minus 12 plus 3, you're going to get 0 over 0. When you plug 1 in, you're going to get 8 over 0. But remember, just because a function's undefined at a value of x doesn't mean that there can't be a limit. We can have a limit even if it's undefined. If there's a hole in the graph, there can still be a limit. So if you were to look at the graph of this rational function and look at these limits again, you can tell from the graph that the limit as x approaches -3, well, there's a hole at -3, and the limit is 1/2. And at 1, there's an asymptote. So when you approach 1 from the left, it goes down to -infinity, and 1 from the right, it goes to +infinity. So I can tell all that from the graph, but when I plugged in, I couldn't tell that. So how am I going to be able to algebraically figure this out without having to look at the graph? So we're going to think back to when we did rational functions in pre-cal and how we found discontinuities of a rational function in pre-cal. And what we started off with was we factored. When we had a rational function, we factored the top and the bottom. So I'm going to rewrite this in factored form. Yes, factoring. You got to know how to do it. I always say calculus isn't hard. The algebra in calculus is what's hard. So when you factor the top, two things that multiply to give you 3 and add to give you 4 are 1 and 3. And on the bottom, two things that multiply to give you -3 and add to give you 2 are 3 and -1. So you can see that the top and bottom have x plus 3 in common. And when you cancel that out, now when you plug -3 in, you're going to get -2 over -4, which is 1/2, which is exactly what we said the limit was as x approached -3. There was a hole in the graph. So the way you can tell there's a hole and that you should do this process is when you get 0 over 0. 0 over 0 means that there's a hole in the graph, and so you should try to factor and cancel before you plug in to try to find the hole. Okay, the other type of problem that you can have other than a hole is an asymptote, a vertical asymptote. So remember, in pre-cal, a non-removable discontinuity called a vertical asymptote, right? And at a vertical asymptote, the y values don't approach a single value. They go to either positive or negative infinity at an asymptote. We can still figure out, though, which one it is, positive or negative infinity, by plugging in values around the number that we're approaching. So like when you look back up where we plugged 1 into this, when you plug 1 in, you get 8 over 0. When you get a number over 0, that means there's a vertical asymptote, which means that you're either going to have positive or negative infinity as your limit. So the way you figure it out, 1 from the left, we're going to plug in something close to this into the simplified version that we got after we factored and canceled. After you canceled out the common factor, this is what was left. When I plug 0.9 in, I get 1.9 on the top and negative 0.1 on the bottom. I have a positive over a negative. This is going to be negative infinity. If I look at the limit as we approach 1 from the right, I know it's positive or negative infinity because when I plug 1 in, I get 8 over 0, which tells me there's a vertical asymptote. But now I plug in something close to 1 but to the right of 1 into my simplified function, and I get a positive over a positive. So it's positive infinity.